starting now, so we're under recording. And if I show you this web page, hopefully you see it. What you're going to notice if you go to Canvas and you click on our Canvas page, I'm gonna situate it so it pops up right away. But right now, if you click the Pages button, you'll see that there's the lecture from Tuesday is on there. So I'm going to reorganize all this hopefully over the next day or so it's a little easier for you to find. I'm also going to upload the whiteboard so that you can have something to look at there as well. Does anybody have any question about homework? Does anybody have any question about whiteboards, lectures, anything while we're at it? Don't forget you can use that chat button if you'd like. I know some of you like to chat instead of talking. That's cool too. If there are no questions, then we'll get back to it. All right, so where did we leave off? So here's what we did last class. Last class, we discussed a topic we touched on even before the break. We discussed improper integrals. And did some examples. Does anybody have any questions about that or any homework problems while we're on it before we do some new stuff? All right, let's do it. So if there's no questions, let's talk about what we mentioned at the end of class. So what we did is we mentioned our ultimate goal is to approximate continuous functions, or let's just say functions in general. So as I saw someone just asked to do a problem. We'll do that in a second. Let's just finish this thought. So what we did is we mentioned our ultimate goal is to approximate functions by polynomials, and let's kind of make that clear with whatever that may mean. So someone asked about a homework problem. So let's do that first before we get back to the approximation stuff. So what number? Someone asked about homework number 6, 1C. So let me pull that up. So if we are on the same page of homework number 1, problem C, is this particular integral. The integral from 0 to infinity of e to the negative 2x dx, but this guy has an x in front of it. So this is the problem at hand. This is an example of an improper integral, and the reason we call it improper is because this upper bound is not a number. We are integrating forever and ever and ever. And so the correct way we want to think about this is we have to use the definition that we talked about Tuesday, and that means we're going to take the limit of some fixed integral. So we're going to let b be some number, we're going to integrate up to b, and then if we get an answer, if we get whatever we get, we're going to then take the limit as b goes to infinity. So this is sort of what's called an improper integral. I alluded on Tuesday that these things show up all over the place in applications, and so that's one of the reasons we touch on them here in calculus too. So if we think about how we'd integrate this, the key observation here is you need to do a u substitution. So what I'm going to do is I'm going to get get a different color here, and then I'm going to sort of come over here and put my draw some things so that we recognize this is sort of scratch work. The correct way to think about this integral is you need to set u to, I'm going to use 2x, and then that means that my du is equal to 2 dx. Now the reason I'm choosing 2x and not negative 2x is that just means I have one less minus sign floating around. So we have to be very careful with this. If I do this, I have to note that this 1/2 anybody have a comment at all? Question? What else do I need to integrate this? Is this an integration by substitution? Anybody? How do you integrate? Ignore the bounds on the integral. Ignore the limit. If I asked you to integrate this 3 weeks ago, how would you integrate this function? This function actually requires
parts.
Yes, it requires parts. That's correct. So
That's
it
it.
actually
Be a substitution and then using natural log.
What's that?
Couldn't there be a
You can't. The substitution's not going to work here. So this thing. So this is a very common mistake. Is oftentimes we think substitution's going to work, and in this case it doesn't. So the correct way to do this actually is to use parts. So the correct way to analyze this function or to compute this integral is to call u x, and then your du is just dx. Then your dv can be e to the negative 2x dx, and that means your v is minus 1/2 e to the negative 2x. So this integral, if I annotate this up here, if this integral, this guy is by parts. The only way to integrate this creature is by parts. Okay, so that means I have to plug this in. I have to be very careful as to not to mess up any of my grouping. So this becomes, if you remember, this is uv evaluated from 0 to b minus the integral from 0 to b of v du. So, does anybody have a question about this in particular? That's the first step. That's really, it's a step that most of us would omit if we've had enough practice. All right, so then now we have to plug this stuff in and evaluate it properly. So uv, this becomes negative x over 2 e to the negative 2x, and that's from 0 to b. And then this becomes plus 1/2 the integral from 0 to b of e to the negative 2x dx. So you'll notice that the minus signs, two minus signs multiplied together give me a plus sign. And so that's how the bottom line is what it is. Does anybody want to ask a question about this? A comment? Again, this is not the easiest of problems. There's multiple levels to this thing. It turns out this is quite an important integral. Okay, so if we go to the next page, we can start plugging in our values and seeing what we can do. So we'll do one step at a time. The first thing I have to do is I have to plug in the bounds on the first portion. So I have this portion here. So what I'm going to do is I'm going to be very careful with how I write this. This is the limit. B goes to infinity. So this becomes negative b over 2 times e to the negative 2b. And then when I plug 0 in, I get 0, so that goes away. So all that remains is this. So again, when I evaluate that first portion between 0 and b, the 0, when I plug b in, I get what's there. And then when I plug 0 in, I'd get 0, so I just ignore it. Okay, so now what I'm going to do is I'm going to be very careful. I'm not going to take my limit yet, because this limit right here is not exactly obvious. At least it requires some explanation. But I can take this integral. This integral becomes minus 1/4 e to the negative 2x, and this is evaluated from 0 to b. All right, so now look, the same thing that occurs, the second guy on the right, this one where my marker's sort of going over, it's very similar to what we had over here, only now there's a fourth, because when I integrate e to the negative 2x, I get negative 1/2 e to the negative 2x. So negative 1/2 times positive 1/2 is negative 1/4. And so with that being said, we can plug in, we have to plug in our b. So I'm going to be very careful here. I'm going to put negative 1/4, and now I'm going to plug in my bounds. So I get e to the negative 2b, and then I get minus e to the 0. Does anybody have a question about this? Again, it's worth repeating, this is not an easy problem by any means. And it's one that you should sort of take as a challenge that, you know, if you can get through it eventually on your own. Okay, so what I want to do now is I want to take one more step at this of cleaning this up. This is negative b over 2 e to the negative 2b. This is minus 1/4 e to the negative 2b. And then this becomes plus 1/4, because if I distribute that 1/4, a negative and a negative 1 becomes positive. Remember, e to anything raised to the power 0 is 1. So that's how I have this 1/4, this e to the 0 goes away. Does anybody have a question about this? Okay, now at this point, we could take the limit, but we have 3 pieces. And the thing is this first piece, this first limit is not an obvious one. The second one is. The second one, it's obvious that e to the negative 2b is going to go to 0. This guy's going to 0. So if we sort of take a different color here, this guy right here goes to 0. And this guy also goes to 0. So this guy goes to 0. And this guy goes to 0. So what we can conclude is that this limit, this integral itself actually is just 1/4. One thing that's worth pointing out, though, is that first guy, the first one with the b over 2, that guy goes to 0. It's not an obvious fact. It's actually one that requires a little explanation, and that is it requires what's called L'Hopital's rule. You might remember that from way back in Calc 2, or excuse me, Calculus 1. So it's worth noting that. So this guy right here, let's actually write it on the first page, or on the next page, because this is an important fact. So this limit this is a basic fact. The fact that this guy goes to 0 this is due to L'Hopital's rule. So you might have to look up what that was. But it's important that you understand the difference here. Does anybody have a question about this? Anybody?
E to the 1 is 0.
No, e to the 1 is 1. Or excuse me, e to the 1 is e. Why are you saying e to the 1? Where do you even see an e to the 1?
Wait, so if you think...
Did I have a typo somewhere? No, I don't. Where do you see e to the 1 at?
No, maybe I'm just confusing myself. Okay, go back to that first page.
E to the 0 is 1. So e to the 0 is equal to 1.
So whenever you're plugging in B, here, go back to the other screen.
This one right here? Or the
one with low
backwards?
Yeah. So if B is going to, so if B is 0.
But B is not 0. We're assuming B is some number larger than 0. And then B is going to go to infinity. See, again, this is these problems, we're putting a bunch of things together here, and some of which you haven't really thought about since way back in Calc 1 at the beginning of the semester. These limits at infinity you really haven't done in a long time, so they're not fresh in your brain. By me writing integral from 0 to b, it's assumed then, context tells us that b is some positive number that I'm going to later let go to infinity. So okay. At no point am I plugging 1 into anything. I'm either plugging b or 0 into an expression. Now, but when I plug 0 in the first expression, if you go back to page 2, if you look at this term down here, remember what this vertical bar means is I plug in b, and then I subtract what happens when I plug in 0. But when I plug 0 into here, this x, this is just going to be 0 times something. So this whole thing becomes 0 if x is 0.
Okay.
That's
All
why
right. Now,
it appears on
here.
the next page. So again, this is by no means an easy problem.
Okay. Now I see where you're getting at with L'Hopital's rule.
Okay, any other questions about this or any other homework problems, particularly these integrals? Going once. By the way, if you want a little bit if you want a little bit of sort of assistance, you know, think about these integrals without bounds before you do the limit process. Think about how you would integrate them beforehand. Okay. Okay, so then let's pick up well, let me give you a couple hints for these. That might be useful. So let me give you a couple hints for the rest of these. So the first one, this is almost similar to what we did on Tuesday. In fact, we showed you the general result. B is just straightforward. There's no tricks. C we just did. So D, think arctan. And then look at the graph of the arctan. Some basic facts. E, this is a U sub. And F is hard and requires deductive reasoning. So you will note, look at the instructions here. I said determine the convergence. I didn't say tell me what they're equal to. I said tell me if they can, excuse me, or diverge. So for part F, this is hard. You might have to look it up if you're really interested in learning about it. It is not one that you can integrate directly. So I'm interested to see how you interpret that. So I'll leave it at that. And if you have more questions, you can ask tomorrow if you'd like, or send me an email. Any other questions on the homework 6? I think we did the differential equations in class well before break. So, okay, if that's the case, then let's get back to what we want to call new stuff. And what were we calling this kind of stuff? Approximation ideas. Okay, so let's motivate with things that you've approximated your whole life. So when you were a kid, you learned something like 1/3 equals 0.333, and then the idea is that this pattern goes on forever and ever and ever. You learn this as a kid. Although, as a kid, there's not much really explained about this. And you kind of, they just hand wave and they say it goes forever. But I would ask you to think about it this way, whatever this really means. Perhaps maybe you guys wrote it differently in your school. Maybe you put like a bar above one of the threes, and that was to represent that the pattern goes forever and ever and ever. Similarly, you learn so you might learn that pi is equal to 3.14159, and then these three dots, these ellipses. Perhaps someone even taught you in school that 1 is the same thing as 0.9999, like this. So what we'd like to do is we would like to ask ourselves, whatever this means. So again, when you encounter this as a kid, you sort of don't think twice about it. You know, when you're probably in like middle school or something, one of the math things in the curriculum is, okay, we're going to talk about rational numbers. And then what they teach you is they'll teach you that if you take any number and divide it by another integer, you can write it as a decimal. And that decimal either terminates or it goes forever and ever and ever. So what is an example of a decimal that terminates? Well, think of 1/2. 1 divided by 2 is the same thing as 0.5. There's nothing that comes after that. Or if you take 1/4, it's 0.25. So what really happens then, if we think about it, is this means we might write 1/3 is approximately 0.333. And we might write pi is approximately 3.14. And we might write 1 is approximately 0.999, etc. Now, here's something even more interesting. Before I go to the next slide, does anybody want to ask a question? Yay, nay, okay. I thought you guys would be so talkative today. Not today. Daryl, are you alive?
Yeah, I'm alive.
All right, good. That's good. How many people are even in this room right now? Oh, 15. That's pretty good.
More than last time.
Well, it's a work in progress. I even tried to invite all my friends to join the party too. Some of them did. I think they got bored after all this. Okay, now some of you might have had some I don't want to say a brave teacher, but a teacher who wanted to teach you some interesting things. Perhaps someone said, something like that 0.333 ellipse 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 is actually equal to, say, 3/10 plus 3/100 plus 3/1,000. And this is not wrong. This is correct. And this is where those words, you know, when you were a young child learning about place value, you would learn about ones and tens and hundreds and thousands, but then you'd also learn about tenths, hundredths. 10,000ths. That's where this comes from. So the problem with this is this suggests that 1/3 is equal to an infinite sort of sum. So this almost seems like something that can't possibly be true. We call it like a paradox. Well, how can something that's finite be also expressed as something that's not finite? Again, why do I say infinite sum? Well, look at the second line on this particular slide. I mean, you're basically saying, take this pattern and do it forever. And if you do it forever, it'll equal 1/3. Well, to be fair, how the hell can you do something forever? Because you'll be dead. And then if your kids take over, they're going to die before it's over. And if their kids take over, you get what I'm saying? It can never, ever, ever end. So how can an endless process actually add up to a finite thing? So that's kind of what we want to tackle. Let's look at a similar so a similar quote unquote paradox occurs here. So let's look at another example of this. So let me draw a square. Let's say this is a square of side equal to 1 has area equal to 1. But now I want to draw the same square, but I want to do it a little differently. Let's assume we're going to chop it up in a certain way. Let's chop it up by cutting it in half. So if I think of this from this perspective, this guy has area 1. Now, if this is also a square of side 1, then this guy has area 1/2. And then if I chop this thing up in a creative way, then this piece right here has area 1/4. And if I chop it up like this, then this particular guy has 1/8. And then I can keep playing this game, but the problem is my pen is making it hard because I can't sort of write what I want to write without messing things up. So I think I'll go one more. So essentially this picture on the right, so if we cut it up, we see that 1 looks to be 1/2 plus 1/4 plus 1/8 plus 1/16. And then the next one would be 1/32. And that thing goes forever and ever and ever. And the point I am trying to make again is that this whole thing is some sort of infinite sum. Now, what's interesting about this is if you went to a calculator and started adding those up, and if you stopped at any point, you're going to get 999 something. You're going to think, hey, it makes sense. But the problem is you can never finish because the right-hand side goes on forever and ever and ever. So this tells us that there's some sort of interplay between infinity and not infinity, and we have to figure out what it is because there's too much intuitive things happening. Now, we've already done this because in many ways the integral in a way of thinking tames infinity, and that's really what we're trying to do here. We're saying we can tame infinity if we're creative enough. Does anybody have a question about that? Comments, questions, anything?
So it's kind of like trying to fold a piece of paper. How many times you can fold a piece of paper?
Oh no, that's actually you're on the different track. You can actually not fold a piece of paper forever and ever and ever. There's actually it's been proven. But the other way to think about it with paper that is in the same idea is if you took a sheet of paper, Daryl, and ripped it in half, and then ripped that in half, and then kept ripping the pieces, eventually you would keep ripping. The piece would be so small that your fingers would not be able to rip it anymore. And so what you would do is you would say, okay, I'm going to go get a microscope and some tweezers, and I'm going to take that little piece that's left, and I'm going to then do that. So do you guys see my face right now?
Yeah.
Okay, so right. So here's what I'm saying. If I have a sheet of paper and I can rip it in half, and then I can take what's left and rip it in half, and then take this piece and rip it in half, and then take this piece and rip it in half, and then this in half, and then this in half. And eventually it's going to be so small that my fingers cannot physically rip it in half. But, okay, so since I can't rip it in half anymore, what I do is I go get tweezers and I use that to rip it in half. And then eventually the piece is so small that my eyes can't see it, so I get a microscope and smaller tweezers, and I keep going. Now, eventually the physical paper's gone, but does the process ever end? The process can never end. Another way of thinking about this that, again, creates a paradox is take any number, take any positive number. If you divide it in half over and over and over again, do you ever get to zero? And the answer is no. So Daryl, every time you take your number, cut it in half, you're going to get a smaller number, but it's never going to be zero. You just keep getting closer and closer and closer. So once again, you have an infinite process that leads to a finite result.
Okay.
So the reason these things occur and the reason that they're actually intuitively sound is the following reason. You have this discrepancy between sizes. Size is relative. So if I take the number 1 and I keep cutting it in half, I get 1/2, 1/4, 1/8, 1/16, 1/32. Eventually that number's so small that for all intents and purposes, it's zero. But we know it's not zero because we can keep dividing it by 2 to get a smaller number. So another way of saying that is that there is no largest number and there's no smallest positive number. And because of those facts, we're able to make sense of infinity. And it's a very strange and fascinating thing. And that's what we're going to try to illustrate to you guys, that the key to approximation is trying to understand infinite processes. So that's where we're at. So if you have a question or a comment, let me know, and let's kind of summarize what we just did this way. All right, so what do the above examples, what should you take from them? Well, they suggest we need to understand sums of the form. I want to add infinitely many things up. So I don't know what they're going to be. So let's give them a name. Let's say a sub 1 plus a sub 2 plus a sub 3 plus. And this process can go forever and ever and ever. Say a sub 100 plus a sub 101, forever and ever and ever. And so this, what we call infinite sum, has a name in math. It's called an infinite series. So you've now learned a new word. It's called an infinite series. So basically I'm saying if I have an endless list of numbers, I can add them together. And we don't call it an infinite sum. We call it a series. So as you guys know, we have shorthand for this. So it's convenient to use what we call sigma notation. You'll remember we can shorthand this. The sum k goes from 1 to infinity. This is the shorthand for what we just wrote down. So you might have to get your mental time machines and go back to Calc 1 when we defined integrals and we use these sums. Now, to study these properly, we must study sequences first. So you've now learned two words. You've learned sequence and series. So that's two new things that are introduced today. Well, maybe you've heard of a sequence before, or maybe even a series before. I don't know. But in the calculus curriculum, this is the first time that we've encountered them. They turn out to be quite important. And in many ways, they're the theoretical foundation of calculus, even though we don't start with them first. Questions, comments? If I just walk away, would anybody know?
Yes.
I took the other class on a tour of the house earlier. Maybe I'll do that for you guys later, if you're interested to see what it's like in the O'Grady household. Although it's chaos. My kids are loud. Amy said she's going to beat them. Things are getting wild here.
You hit up the liquor store beforehand, right?
Did I not? It's closed.
Should have went
Liquor
the day
stores,
before they closed.
liquor stores are closed. They closed them all. They're not essential operating businesses.
Should have went before they closed.
Oh, don't worry, Daryl. I did. All right. So what we need to do now is we need to study sequences. So you have to study sequences in order to properly study series. And if we want to study approximation as a sort of subject in and of its own, we have to start with these things. So let me write that down. So sequences in series are the basic tools for approximation, or let's just say approximating. So essentially what we're telling you is you've kind of been using ideas in math a lot, but you've never really been given the precise meaning of them. This is nothing new to you. How often did you guys use the word area in your life, but you never knew what it really meant until calculus? So that's not the end of the world. Okay, so that's where we're going to go right now. We're going to make some definitions. So here's the baby definition. What is a sequence? A sequence is an ordered list of numbers. So the word sequence in math is very similar to what it means in the English connotation. It's a list of numbers. So that is a sequence. Now, we use braces to empathize. I did that in class. That was funny. So we use braces to show the object, and I'll put that in quotation, is a sequence. So what do I mean by that? Well, we might write something like 1/2, 1/4, 1/8, 1/16, 1/32. That is an ordered list of numbers. I put braces around it so that you guys know it's a sequence. Each number is called a term. So, and we refer to them as first, second, third, etc. So the first term, the second term, the third term. So it's convention to use subscripts. So A1, A2, A3, A4, etc. You could even say, okay, this is the 100th term, the 101st term. And then, of course, the nth term is A sub n. And so as you know from previously, what we do is we call the subscript that has a name. It's called the index. Does anybody have a question? Okay, so what do? We don't like to write it like that. So for short, we might write A sub n in braces and say n starts at 1 and goes to infinity. And then we know that that means this.
or any subscript?
What's that? Say that again.
Is n the index or any subscript?
No, and okay, so it depends on context. So what we're saying is the index is just the subscript. So it could be 3, it could be 116, it could be K, it could be J, it could be N. It doesn't matter. We're just saying that that's what we call the subscripts. They're called the index of the sequence. That might be not apparent why it needs a name right now, but I think you'll see soon enough you'll see that it's helpful just to have that name. It's mostly we give it a name so we can refer to it. It's really what we do, just like we give you guys names, and I have a name. And we name things like, hey, this is a phone. These are, earphones or whatever. This is a pen. We give things names so it's easy to refer to. So reason I'm telling you the index is just so you know exactly, hey, we're going to refer to this. Maybe the index is J for this one. Maybe for this sequence, it's K. That's all. Sort of like you could think of it as like when you have a function f of x, we say x is the variable. That's all. It's just a name for it. Does that make any sense? I don't know. I think it'll be a little more clear later why we do that. It might not be clear right now. So what are we interested in? Well, we're not just interested in any types of sequences. So in this class, so what we are interested in sequences that have certain, how do we say it, patterns. So pattern can be very arbitrary, so I'm just going to put it in quotations. That can mean lots of things. So for this reason, what we do is we study sequences that can be generated in one of two ways. So the first way, which is most common that we care about, is explicit formula. And the second way is what's called a recurrence relation. So we're going to give examples of both of these in a second to see what I mean. Because right now it might not be clear what the heck am I talking about. What does he mean to generate? A good way to think about this is as follows. I'm not just interested in any list of numbers. I mean, you could just sit there and randomly pick numbers. I don't care. Those are of no interest to us in calculus. What we're interested in are lists of numbers that are generated in a certain way. And the way they're generated come from different things we might do. Maybe we take derivatives, or maybe we do something. So we're generating these in a certain way. Let's do some examples, and hopefully this makes sense. So how can I generate some things that I've written before? Well, let's look at some examples. The first one can be something like, how do I generate the even numbers? Well, I can say, okay, let's look at all numbers of the form 2 times n, where n starts at 1 and goes to infinity. So what does this mean? This means I have 2, I have 4, I have 6, I have 8, I have 10, I have 12. And let's be very clear how I'm getting these numbers, because this is probably new to most of you. So let me get a different color. If you want to think about this, you can think about this as this is a sub 1, this is a sub 2, a sub 3, etc. And what is a sub 1? Well, that is just 2 times 1. And what's a sub 2? That's just 2 times 2. And what's a sub 3? That's 2 times 3. So that's one way you can interpret this sequence. So a general, a way of thinking about this that's even more clear is, look at the nth term. It satisfies a sub n has the explicit formula, it's 2 times n. So one of the things that makes this difficult is that most of us have not really studied these kinds of things before. It's kind of all new. We're not solving equations right now. We're not taking derivatives. We're kind of thinking about how we generate lists of numbers. And so the notation is abstract and it's foreign. So it makes it hard for us to learn. It's going to take an effort for most of you to learn this. That's just what it is. Does anybody have a question or a comment? Okay, so that's the list of even numbers. Now let's do another example similar to what we did earlier, if I may. Oh, by the way, let's go back. I want to go back because this is important to note. So note this is an explicit formula. You can generate the 400th term just by using this formula. Let's look at another creature. Someone had a question about recurrence in programming and recurrence relation, and the answer to that question is yes. So if you look at the chat, you will see. Let's look at another one that's explicit, because we did this one before. Let's take the sequence 1 over 2 to the power n. And now we're going to start n at 1 and go to infinity. And so what's the first guy? The first guy is when n equals 1, so I get 1/2. When n equals 2, I get 1/4. When n equals 3, I get 1/8. Then I get 1/16, 1/32. So if we play the same game we did before, and you want to think about this from a more abstract point of view, this is a sub 1, a sub 2, a sub 3, etc. And this is 1 over 2 to the 1, 1 over 2 squared, 1 over 2 cubed. And here the nth term. What is the nth term? The nth term, a sub n, is just 1 divided by 2 to the power n. And this is explicit. Does anybody have a question about this? So these are two examples of explicit sequences. Now, once again, you don't learn this by watching me. You don't learn it that way. You learn it by doing it. So you have to get practice problems, blah, 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 blah. All right, so let's do an example of a recursive sequence because those are important as well. So let's do our third guy. So the third guy we might have, by the way, sometimes you can generate things in more than one way. So we can generate So the odd numbers like so. We can say a sub 1 is 1. And then we can say a sub 2 is a sub 1 plus 2. And then we can say a sub 3 is a sub 2 plus 2. So in general, we can say the nth term in a sequence is given by the previous term plus 2. So this is called a recurrence relation. So for example, what is this equal to? Well, this becomes, if I sort of, and if any of you have ever had any experience programming, you'll see why these things are very useful. They show up all kinds of applications because it's a very quick way of generating things. So what is this equal to? This is equal to 1. What's this guy equal to? Well, this is 3. This guy is 5, etc. So that is one way to generate the odd numbers. Okay, here's another example. Does anybody have a question about this, by the way? So here, this example 3 is one we're doing where we're basically saying, here's a way to generate numbers. Sometimes we want to do the opposite thing. Sometimes we have a list of numbers and we want to know how it was generated. So let's do an example of that. So for the fourth example, let's think of this. So we can generate this sequence. Let's do this. How about 3, 6, 12, 24, 28. Excuse me, not 28. That makes no sense. This would be 48. So it might not be obvious to you how to generate this sequence, but you can generate it in the following way. We can generate this by setting A1 equal to 3, and then A sub n equal to the previous guy times 2. So you start with 3, and then you generate the second one, the third one, the fourth one using this formula. Notice that if that list of numbers, every number is 2 times the number to the left. 6 is 2 times 3. 12 is 2 times 6. 24 is 2 times 12, so that we've generated this sequence. If you want to blow your mind, and of course I know you're all nerds and want to do this, so there is this, I'm going to show it to you in a second, if I get my whiteboard back. What you can do to blow your mind is you can you can Google the encyclopedia of sequences. So a bunch of nerds for like so many years have been putting a database together of everything humans know about this, and I will show it to you right now, because why not? What else are we going to do with ourselves? So right now you should see a web page. It's the online encyclopedia of sequences. And it was started in the 60s by this nerd, Neil Sloan, who was a guy who worked at IBM. He was a mathematician. And essentially, you can put your sequence in and see what happens. So what did we have? We had 2, 6, 12. I mean, this is obviously a well-known sequence. And you can see everything you ever wanted to know about this sequence. Actually, that is not the one we wanted. We need to go one more step. We need to go 48. So you'll notice that there's many sequences that have these first few terms, and so you have to go find which one it is. This is pretty wild if you're bored. Anyhow, you're probably like, I don't care. But anyhow, if you are bored and want to do something, there you go. What happened to my whiteboard? There it is. Does anybody have a question about this? All right.
How are we tying this into
Yeah, you're
indefinite?
gonna have to wait for tomorrow to see how this connects. But that's a great question. So let's sort of try to start getting the ball rolling. So questions you might have. What patterns? You would see that all 4 of those guys have patterns. So what patterns do we care about? And more importantly, Daryl, how is this related to series? So how is a list of numbers related to adding the numbers in a list? So those are 2 very important questions. And to answer them, we have to talk about what's called an old friend of yours, the limit. So we're not going to do that today because we're out of time, but we can end with this. It's perfect. They give us 20 slides. Here we go. Here's 20 slides. So to answer this, we need to study limits of sequences. Now, luckily for us, this is the same type of limit we've been studying. So luckily, we know a few things about limits. So, and we will see this tomorrow. All right. If you guys don't have questions, oh yeah, someone wants me to go back a slide. I can do that. Is this the one we wanted, or do we need to go back even more? Don't forget, all these slides will be available on Canvas. You will be able to check them out. You will be able to download them, print them, whatever you want. Does anybody have a question? All right, if you guys don't have questions, I am going to stop the recording and I am going to exit the meeting. So if you guys have questions, now's a good time to speak up. Otherwise, I will see you guys hopefully tomorrow. So don't forget, this link will not work tomorrow. You need a separate link for Friday because the times are different. So look forward tomorrow morning to getting an advertisement, not an advertisement, but an announcement on Canvas for the code. All right, guys, I will see you. Oh, Oh, someone wants the last slide. Okay. I'm going to stop recording, but I'll